Welcome to my channel. This time we're looking at another application of the cross product in finding the volume of a parallelepiped. So I would run it, and this one is just is a figure with how many faces? These are 6 faces. And what we discover is that the opposite faces are parallel to each other. And all the faces are made of parallelograms. So you can see this face is made of a parallelogram. This face is also made of a parallelogram. This face is a parallelogram. This other one is a parallelogram. And that one is also a parallelogram. So the question we begin with is to prove that the area of this figure is given by the magnitude of the scalar triple product. The magnitude of the scalar triple product. So that is how we get the area of this figure. So we just want to prove that it's true. But what we know is that this is the base. Of course, we know the area of the base. From our previous video, we looked at how to get the area of a parallelogram. And we said that the area of a parallelogram is given by the magnitude of the two sides. The magnitude of the two sides. So that if the parallelogram, this parallelogram has alpha this side and beta this other side, then the area of this will be given by this. But now, what we want is to show that the volume is given by, what we know is that volume is supposed to be given by area, base area times height. Base area times height. And our height is this, h. And our base area is this. So how do we then show that volume is given by that? That means you just need to substitute. You just need to substitute height. So that volume is now given by height times this. But how do we get height? What you notice that this height is a component of this mu. Is a component of this mu. So let's see how I did to show that the volume is given as statement. So just to repeat what I've already said, is that a parallelepiped is a 6-sided solid, and the sides are parallelograms. Those faces are parallelograms, and the opposite parallelograms are identical. And so the volume will be given by base area times perpendicular height. And the base area is known to us, is this. And so, for us to get height, what we need to notice is that the height is a component of mu, and it's in the direction that is perpendicular to the plane that contains alpha and beta. So since height is a component of mu and is perpendicular, is in the direction perpendicular to the plane containing alpha and beta, we can say that height is given by this. Height is given by this. It's a component of mu and is in the direction perpendicular to this. So this is a unit vector. This is a unit vector. You see, you remember that this alpha cross beta over alpha cross beta magnitude of that. You remember that this is a unit vector perpendicular to the plane of alpha and beta. This is a unit vector perpendicular to the plane of alpha and beta. And so that is how we get height. That's how we get height. So just substitute that in our formula, where we have base area times that times height. So let me just scroll it down. So volume is height times base area, but height is this. Height is this. So I've just substituted the height by this. So mu dot alpha cross beta over the magnitude of alpha cross beta, and then times this area of the base. So discover that these are common, we cancel out, and what we are left with is mu dot alpha cross beta as the volume of this parallelepiped. Now, how does the modulus come in? The modulus comes in because we know that this scalar triple product can be negative. And since it can be negative, we only need to get the modulus of it to have the volume. So the modulus of this is the volume, and that is what we are required to show. And we look at an example. So the example is, find the volume of a parallelepiped ABC if A is this, B is that, and C is this. So what you notice is that we already have the formula that for us to get volume, and we are given ABC, we only need to get C dot ABC, no, C dot A cross B, and then get the modulus of that. That gives us the volume. You can even take A dot B cross C and get the modulus of that. There's no problem. You still get the same result. Or you may want even to take B dot A cross C and get the modulus of that. And there's no problem with that. You'll get the same result. So let's do that. We are ready now to do this from our previous video where we looked at finding the scalar triple product. So we're getting the determinant of the coefficients C1, C2, C3, A1, A2, A3, B1, B2, B3. And this is the values of C. So C is 2, 3, 1. And A is 2, 4, 4. And B is negative 4, 4, 7. So to find the determinant of this is easy to us because we have various ways of finding the determinant of matrix. It's just a 3 by 3 matrix. So let's click on the easier method we've been using from the start of our video, where I take the entire matrix here and place it here, and then take the first 2 rows in the columns and add them here. And then multiply along these blue diagonals and add the results. You can see this will be 8 times 7, which is 56. This will be 4 times 4 times negative 4, which will be negative 48. And do for this one. And then multiply along these right diagonals and subtract the result. For instance, this would be 14 times 3, which is 42, and subtract the result, 42. This will be 16 times 2, which is 32, and subtract. So when you do that, you find that this scalar triple product is negative 42. And so the volume should be the magnitude of this. So the volume is the magnitude of that, which is 42 units cubed. Let's look at another example to make it clear to us. The question is, find the volume of a parallelepiped with the edges. These are the edges. So again, what we're supposed to do is just to get the scalar triple products and then get the modulus of the answer. And so the same thing, I have the coefficients of alpha, they're here, 2, -3, 5. The coefficients of beta, which are -4, -4, 7, and the coefficients of mu, which are -1, 3, -2. And we use the easiest way to find the determinant. The whole of this matrix, place it here, and then the first two columns add them here. Multiply along the blue diagonals as you add the results. This is the first 3. And then multiply along the red diagonals as you subtract the result, the last 3. 24, -42, and -20. That gives you -61. So the modulus of -61 is 61 units cubed. And that gives you the volume of the parallelepiped. And so that is how we use the triple products to find the volume of the parallelepiped.